So this is the electric field, delta V divided by delta D. And I'm going to use the Van de Graaff generator for this. So I'm going to go ahead and dim the lights. I'm going to take them all the way down. We'll just be illuminated by the blue glow of the slide. And I'm going to turn this on. And when I do that, when I turn on the Van de Graaff generator, it charges up to a certain potential. This develops a certain potential, okay? So right now, that's at a certain, this is a certain potential. And this is at 0 volts. I define 0 volts as being the ground. And by the ground, I mean electrical ground. And by electrical ground, I mean the earth, actually. Somewhere there's a rod stuck into the earth, and this is connected by a wire to it. This is at 0 volts. That's at some voltage with respect to it, okay? Now, so that's the mountain, and this is like the bottom of the mountain. And the height of the mountain, this potential doesn't change. But if I bring this closer, delta D, the distance between these two, gets smaller. As that happens, what happens to the electric field as delta D decreases? It grows. And at some point, the electric field becomes bigger than the electric field necessary to ionize air. And when that happens, a spark jumps. So what I want to do is I'm going to do that again, and we want to get a rough estimate of how much distance is required for that. Okay, rough estimate of the distance. Bringing it in, how close do these have to get before the spark jumps? I'm thinking 6, probably 6 inches. 6 inches is probably about 15 centimeters, would you say? And if I try it on this side, let's see if I get, oh yeah, I get a little bit farther. That's probably about 20 centimeters is what I'm thinking right about here, 20 centimeters. It looks bigger if you're closer to it and you're holding this device here, okay? So yeah, probably about about 20 centimeters is what I'm thinking. And I'll turn this off, and as we've seen before, I can just discharge it like this. That's the point I want to come back to. But I want to do a calculation. Here's the calculation I want to look at. Let's assume that the electric field is uniform between the two spheres. Not exactly, but we can take that as a pretty good approximation. When a spark jumps, we can assume the field between them is 1 times 10 to the 6 volts per meter. That's how big the electric field has to be in order to ionize air. The field gets big enough, it just breaks down the air. The air ceases being an insulator, begins being a conductor, conducting path, spark jumps from one sphere to the other. Question, what's the potential difference between the two spheres at that instant? Well, we can work that out. We know delta V is equal to the electric field times delta D. So the electric field is the electric field necessary to break down the air, 1 times 10 to the 6 volts per meter, times delta D, and we figured it was about, I think it's about 20 centimeters is what I'm guessing, so 0.20 meters. 1 times 10 to the 6 volts per meter times 0.2 meters, 200,000 volts. 200,000 volts. If that's true, why is it possible that I can just like charge this up and put my hand here? That's 200,000 volts. So I can touch this 200,000 volt object without suffering ill effects. How come I can do that? And that has to do with the second question, okay, is how much charge is transferred. There's some more things to be said about this, but ultimately, how much something hurts is less a function of the potential difference than it is of how much charge is transferred. In this case, the amount of charge isn't that great. 10 microcoulombs is all that you have on the sphere. And one way that we can get a sense as to how little that is this way. I want to compute how much change in potential energy would it be if I transferred 10 microcoulombs from one sphere to the other. So imagine I could take that entire charge on the one sphere, transfer it to the other. And when this is totally charged up, it's got about 10 microcoulombs on it. I transfer it entirely to the other charge. What would be the change in potential energy? Now I'm cheating a little bit because I'm assuming that when the charge is transferred, the electric field remains. In fact, the electric field goes away. So it's a little bit of a cheat. So that'll give us, if anything, an overestimate. Well, we've seen that the difference in potential energy is equal to Q times delta V. The charge, 10 microcoulombs, so 10 times 10 to the minus 6 coulombs, times delta V, 200,000 volts per meter, or 200,000 joules per coulomb. I'll switch to my other unit for the I'll switch to my other unit for volts, and I end up with an energy of 2.0 joules. How much energy is 2.0 joules? Here's about 2 joules. If I take this little hamster, raise it up about this far, and drop it on my toe, that's about 2 joules of energy transferred to me. And that was a relatively gentle collision. The total amount of energy involved here, not that big. Similarly, the total amount of energy transferred here is not that large. And that's one measure of how small it is. And the reason why it's small is not because the voltage is small. The voltage is big. It's just you don't transfer very much charge. You can think about it. A lot of charge drops from there to my arm. A charge drops from there to my arm, and it's dropping from a great height, but it's not very much weight. You could think about it that way. And so the net result is just not that scary. It's not that upsetting.